The research paper explores the non-Einsteinian viscosity reduction in boron nitride nanotube (BNNT) nanofluids. This study delves into the rheological properties of BNNTs at ultralow concentrations, ranging from 0.1 to 10 parts per million ppm, in the presence of methane at low temperatures. The findings reveal a significant viscosity reduction of up to 29% at 10 ppm, which is comparable to similar studies on other nanofluids. This research highlights the unique properties of BNNTs in reducing viscosity, particularly in the presence of methane, and their potential applications in various fields. The non-Einsteinian behavior observed in this study could be attributed to the nanotube's surface area and its interaction with the surrounding fluid, leading to a more complex rheological behavior than what is predicted by Einstein's theory. The paper emphasizes the importance of understanding the rheological properties of nanofluids, as they play a crucial role in determining their potential uses. For instance, the ability of BNNTs to reduce viscosity could enhance the flowability of fluids, making them more suitable for various industrial processes, such as oil extraction and transportation, or in biomedical applications where fluid flow is critical. Moreover, the study's findings suggest that the interaction between methane and BNNTs may lead to novel methods for methane storage and transportation. By utilizing the unique properties of BNNTs, researchers could develop new strategies for managing methane, a potent greenhouse gas that contributes significantly to climate change. In conclusion, this research provides valuable insights into the rheological behavior of BNNT nanofluids and their potential applications. Further studies are needed to fully understand the underlying mechanisms and to explore the full range of possible uses for these materials. Nanoparticles, with dimensions in the order of 100 nanometers or smaller, have numerous applications, including pharmaceuticals, biosensing, and carbon capture. Pure carbon-based nanoparticles like graphene nanoflakes, GNF, and multi-walled carbon nanotubes, MWCNT, are hydrophobic, but their surfaces can be functionalized with oxygen or nitrogen groups to introduce hydrophilic properties, improving water solubility and dispersion. The conservation of energy equation, considering mechanical effects, includes the mechanical work term and its viscous contribution to the energy balance. This viscous dissipation represents the conversion of kinetic energy to heat through internal friction in the locally sheared fluid. The internal friction arises from molecular interactions in the sheared fluid. One would expect that the addition of particles to a fluid would increase the internal friction, leading to greater viscous dissipation, and thus result in a greater effective viscosity in the mixture. However, previous work has reported non-Einstein-like viscosity reduction in nanoparticle-polymer blends. For instance, Roberts et al. Reported a decrease in viscosity in a blend of poly-dimethylsiloxane with trimethylsilyl-treated silicate nanoparticles. Similarly, McKay et al. Used a suspension of polystyrene, PS, nanoparticles in linear polystyrene, PS, at low nanoparticle concentrations to study this effect, reporting a reduction in viscosity that disagreed with predictions from Batchelor and Einstein's theoretical models. More recent studies have reported non-Einsteinian viscosity reduction in ultra-low concentration aqueous carbon-based nanofluids of GNF and MWCNT. These systems are fundamentally different from the nanopolymer blends, and the mechanism leading to viscosity reduction may also be different. Hydrophobic nanoparticles such as GNF and MWCNT are sparingly dispersible in water and require surfactants to avoid agglomeration in solution. Alternatively, the hydrophilic functionalization of nanoparticles results in nanofluid solutions that can remain dispersed for up to 2 years. In the works by McElligott et al., the GNF and MWCNT were functionalized with hydrophilic carboxyl, hydroxyl, and ether oxide groups through a thermal plasma decomposition process. They report a viscosity reduction of upward of 29% upon the addition of oxygen functionalized GNFs, O-GNF, at ultralow concentrations, 0.110 ppm. In the current section of the research paper, the focus is on the viscosity reduction in boron nitride nanotube nanofluids. The primary causes of this reduction are identified as the disruption of hydrogen bond networks and the enhancement of density fluctuations. This phenomenon is attributed to the interaction between the nanotubes and the surrounding fluid, which leads to a decrease in the fluid's resistance to flow. The disruption of hydrogen bond networks occurs when the nanotubes interfere with the intermolecular forces within the fluid, leading to a more disordered structure. This results in a decrease in the fluid's viscosity, as it becomes less resistant to shear stress. The enhancement of density fluctuations also plays a crucial role in reducing viscosity. As the nanotubes move through the fluid, they create local variations in density, causing the fluid molecules to rearrange and form new structures. These fluctuations lead to a decrease in the fluid's resistance to flow, resulting in lower viscosity. The paper further explores the implications of these findings for various industrial applications, such as heat transfer enhancement and fluid flow improvement. By understanding the mechanisms behind viscosity reduction in nanofluids, researchers can develop more efficient and effective methods for enhancing fluid properties. The study's results have significant implications for the design and development of new materials and technologies. For instance, the use of boron nitride nanotubes in cooling systems could lead to improved heat transfer rates and reduced energy consumption. Similarly, the application of these nanofluids in oil extraction processes may enhance the flow of crude oil, increasing efficiency and reducing costs. However, the paper also notes some limitations and areas for future research. For example, the long-term stability and potential toxicity of boron nitride nanotubes in different environments need to be investigated further. Additionally, the optimal concentration of nanotubes required for achieving maximum viscosity reduction without compromising the fluid's other properties remains unclear. Overall, the study provides valuable insights into the mechanisms underlying viscosity reduction in boron nitride nanotube nanofluids, paving the way for further exploration and development in this field. The research on boron nitride nanotubes, BNNTs, focuses on their production, characteristics, and application in reducing non-Einsteinian viscosity in nanofluids. The BNNTs were produced and characterized with an 80% purity using a three-stage purification process involving removal of hydrophobic impurities, size reduction, and bromine treatment. This process added hydroxyl and amino groups to the BNNTs, enhancing their water solubility. The experimental procedure involved loading a rheometer's high-pressure cell with BNNT nanofluid at various concentrations and controlling the temperature and methane pressure to ensure precise test conditions. The paper explores the reduction in viscosity of water-based BNNT nanofluids, with a specific focus on the impact of temperature. It is established that an increase in temperature generally leads to a decrease in the viscosity of liquids, including nanofluids, due to higher molecular kinetic energy and enhanced Brownian motion. To measure viscosity, the study utilized the Anton Par MCR 302 rheometer under various conditions, encompassing different temperatures and BNNT concentrations. The findings indicate a linear decrease in viscosity with temperature for both pure water and BNNT nanofluids, suggesting no significant temperature effect on viscosity for the concentrations examined. However, the addition of BNNTs resulted in a non-Einsteinian viscosity reduction, which will be elaborated upon in the following section. The concentration effect of boron nitride nanotubes, BNNT, in water under an air atmosphere is discussed. It is observed that all BNNT concentrations above 0.1 ppm exhibit a reduced viscosity compared to pure water at equivalent conditions. The measured viscosity was approximately 11% lower than pure water on average across temperatures for 0.5, 1, 5, and 10 ppm systems. Conversely, the viscosity of the 0.1 ppm BNNT nanofluid was measured to be approximately 5% higher on average across temperatures. The optimal cost-effect relationship was found at 0.5 ppm, achieving approximately the same viscosity reduction as the 10 ppm system. The results are compared to O-GNF and O-MWCNT systems, highlighting differences in concentration effects due to surface chemistry and geometric differences between nanoparticles. The addition of methane atmosphere is also discussed, showing a weak effect on viscosity in pure water and a similar effect in BNNT nanofluids. The research investigates the application of machine learning algorithms to predict protein structure from amino acid sequences. It proposes a novel approach, integrating both primary and secondary structure predictions to enhance accuracy. The methodology involves training a neural network on a dataset of known protein structures and sequences, leveraging both local and global sequence features. The model's performance is evaluated using metrics such as root mean square deviation and precision. The study highlights the potential of this approach in accelerating protein structure prediction, a crucial step in understanding protein function and disease mechanisms. In the realm of non-Einsteinian viscosity reduction, researchers have been examining the effects of boron nitride nanotube (BNNT) concentration and methane on nanofluid viscosity. The findings indicate that a 10 ppm nanofluid exhibits the most significant reduction in viscosity, reaching up to 29% at 5 megapascals. This effect is notably stronger in three-dimensional nanotubes compared to two-dimensional nanoflakes, possibly due to their geometry. The higher probability of flow-induced alignment in nanotubes may contribute to sustained reduced viscosity before drag forces dominate at higher concentrations, leading to increased viscosity and a return to the Einsteinian regime. The authors revisit their previous hypothesis on the source of non-Einsteinian viscosity reduction, suggesting that at ultralow concentrations, particles similar in size to the molecular size of the suspending liquid may not contribute sufficient internal friction to increase the effective viscosity of the bulk fluid. Hydrophobic interactions could disrupt hydrogen bond interactions in the base fluid, and the presence of nanoparticles may enhance density fluctuations, improving energy dissipation in the nanofluid and reducing its viscosity. To further understand the effects reported in this and previous works, computational work such as molecular dynamics simulations is recommended. These simulations would examine molecular interactions between nanofluid components and the base fluid, providing insight into the mechanisms underlying the observed phenomena. Figure 4 illustrates the relative viscosity of water-based BNNT nanofluid at various concentrations, demonstrating a reduction in viscosity with increased loading of BNNT in the nanofluid. This research paper delves into the non-Einsteinian viscosity reduction observed in boron nitride nanotube (BNNT) nanofluids, a significant deviation from the Einstein model that predicts a linear increase in viscosity with nanoparticle concentration. The study compares this phenomenon with similar reports on graphene nanoflakes (GNF) and multi-walled carbon nanotubes (MWCNT) nanofluids. The results show that BNNT nanofluids exhibit a more pronounced non-Einsteinian effect compared to GNF and MWCNT nanofluids at similar concentrations. This difference is attributed to the distinct geometric characteristics and surface chemistry of the nanoparticles involved. The presence of a methane atmosphere was also tested, revealing that the 10 ppm BNNT nanofluid demonstrated the highest effect on viscosity. This is likely due to the hydrophobic surface of the nanoparticles, which shuttles methane into the liquid phase, introducing hydrophobic methane bubbles that further disrupt hydrogen bond networks. Future work is suggested to explore the limits of the non-Einsteinian effect by considering higher BNNT concentrations. Investigating nanoparticles with different geometries and amounts of functionalization, such as fullerenes, graphene oxide, and carbon dots, is also proposed. Moreover, computational studies, like molecular dynamics, are needed to understand the molecular interactions between nanofluid nanoparticles and the base fluid. These interactions could help identify the molecular scale sources of the macroscopic non-Einsteinian viscosity reduction observed in this and previous works. The authors acknowledge the support received from various organizations, including the Digital Research Alliance of Canada, Calcul Quebec, and West Grid, for computational resources, expertise, and technical support. They also thank the National Research Council of Canada for providing the BNNT samples used in this study. Financial support for the work was provided by the Natural Sciences and Engineering Research Council of Canada, NSERC, Fonds de recherche du Québec Nature et Technologies, FRQNT, the McGill Engineering Doctoral Award, MEDA, and the James McGill Professorship. The non-Einsteinian viscosity reduction in boron nitride nanotube nanofluids is the primary focus of this research, which examines the effects of plasma functionalized carbon nanotubes on methane hydrate systems. The research paper delves into the non-Einsteinian viscosity reduction in boron nitride nanotube nanofluids, examining the impact of nanoparticle concentration on the thermophysical properties of CuO-propylene glycol nanofluids. It also explores the preparation and properties of iron-3 oxide propylene glycol nanofluids, as well as the transport properties of nano-manganese ferrite propylene glycol dispersion and the rheological characteristics of CeO2, aluminium oxide, and their hybrid mixture in ethylene glycol base fluid across a wide range of temperature and concentration. Furthermore, the study investigates the effects of T3C2TZ-MXene nanoparticle additive on fluidic properties and tribological performance. The synthesis and in situ oxygen functionalization of deposited graphene nanoflakes for nanofluid generation are also discussed. Additionally, the dynamic viscosity of methane and carbon dioxide hydrate systems from pure water at high pressure driving forces is examined. The paper draws upon the investigations on the theory of the Brownian movement by Einstein and the gas absorption mechanism in catalytic slurry reactors by Alper et al. The research concludes with a discussion on the potential applications of these findings in various fields, such as energy storage, heat transfer, and biomedicine, emphasizing the importance of understanding the unique properties of nanofluids for their efficient utilization. In the context of boron nitride nanotube nanofluids, viscosity reduction is a critical aspect of their behavior. To provide a comprehensive understanding of this phenomenon, two supplementary figures, Figure A1 and Figure A2, are presented. These figures investigate the viscosity effects of pure water systems and water-based BNNT nanofluid, respectively, in a methane atmosphere at various pressures. Figure A1 examines the temperature and pressure effects on the viscosity of pure water systems. The results are presented in two subfigures. A displays the temperature effect, and B shows the pressure effect. The error bars represent 95% confidence intervals, and linear regressions are provided for each condition. This figure serves as a baseline for comparison with the nanofluid systems. Figure A2 focuses on the viscosity of water-based BNNT nanofluid at a 0.1 ppm concentration in a methane atmosphere at several pressures. Similar to Figure A1, the results are presented in two subfigures. A illustrates the temperature effect, and B displays the pressure effect. Again, the error bars represent 95% confidence intervals, and linear regressions are provided for each condition. This figure highlights the viscosity reduction in the presence of BNNT nanofluid. These supplementary figures provide crucial context for understanding the non-Einsteinian viscosity reduction in boron nitride nanotube nanofluids, a key aspect of the research. The findings presented in these figures are essential for validating the experimental design and supporting the conclusions drawn in the main manuscript. Viscosity reduction in water-based boron nitride nanotube, or BNNT, nanofluids is a critical parameter in various industrial applications. This study investigates the effects of temperature and pressure on the viscosity of BNNT nanofluids at a 1 ppm concentration in a methane atmosphere. The results show that increasing temperature and pressure significantly reduce the viscosity of the nanofluid. Specifically, a temperature increase from 20 degrees Celsius to 40 degrees Celsius at a constant pressure of 1 atmosphere resulted in a viscosity reduction of approximately 20%. Similarly, a pressure increase from 1 atmosphere to 10 atmospheres at a constant temperature of 20 degrees Celsius led to a viscosity reduction of around 15%. Linear regressions were performed to analyze the data, and error bars representing 95% confidence intervals are provided to ensure the accuracy of the results. The data was collected by MMRG, Hydrate Tech, and Marić Labs. These findings have significant implications for the design and optimization of BNNT nanofluid-based systems, such as heat transfer and lubrication applications. The observed viscosity reduction can lead to improved system efficiency, reduced energy consumption, and enhanced overall performance. Further research is needed to explore the underlying mechanisms of viscosity reduction in BNNT nanofluids and to investigate the effects of other parameters, such as concentration and surface functionalization, on their rheological properties.